This is video number 4. Last time we analyzed the velocity equation. Uh, v squared equals omega squared, a squared minus x squared, a being the amplitude of the motion, simple harmonic motion. Right, now we have an equation that is describing the acceleration of the motion, and now we have an equation that is describing the velocity of the motion. Now we need to know what the displacement is. So how do you, what sort of a function will describe the displacement? Now we can use this equation. I'm going to take the square root on both sides. We get v equals plus or minus omega a squared minus x squared. We have a square root here. Right. So just for the integral, I'm going to take the positive quantity here. So v equals omega a squared minus x squared, and v is replaced by dx by dt because we need to find the x displacement now. What is x? So we replace this with dx by dt. Now I'm going to cross multiply this dx. This part goes to the denominator here, square root of a squared minus x squared, and dt goes to the top, omega dt. Now on the left side you have only x terms, a is a constant, doesn't matter. On the right hand you have only t terms, omega is a constant, so we can integrate both sides. Now this is an integral. The easiest way to evaluate this integral is to use a substitution, or you can just memorize the formula. This is the formula for sine inverse function, the derivative of sine inverse function. But let me just talk about the substitution method here. So by substitution, what we do here is that this looks like a complicated integral here. So using the substitution, what we do is we convert this integral into something that is simpler for us to solve. Right. Now what is a substitution? So x, whenever you have something like this, right? In the denominator you have a square root a squared minus x squared. Then the common substitution is x equals a sine theta. A sine theta. Why? So when you substitute this, when you square this, you get a squared sine squared theta. So you can take out a squared, then inside the square you get 1 minus sine squared theta. So 1 minus sine squared theta is cos squared theta. So that will get rid of the square root. So that is the idea behind using this substitution. So if this is x equal a sine theta, this implies theta equals sine inverse of x divided by a. Sine inverse of x divided by a. Now if I differentiate this, I get dx. Small increment would be increment in x, a cos theta d theta. So what I did here is I differentiated this with respect to theta and rearrange it and finally obtain this one. So when you use the substitution, what we do here is we convert all the x variables into that substituted variable. So we came up with a substitution for x. Now we came up with a substitution for dx, simple quantity. So now we can rewrite this. So dx is a cos theta divided by, this becomes a squared minus a squared sine squared theta squared d theta. So on the right hand side you can integrate. So this becomes omega theta plus an integrating constant. You can take out an a squared, then this a cancels out this a, and in the denominator you have 1 minus sine squared theta, which is equal to cos squared theta. The square root of cos squared theta is cos theta. So on the top you have cos theta, so those two cancels out and you are left with only d theta. See how simple this is. By using a substitution, we have converted a complicated integral into something much simpler for us to solve. So d theta gives you theta equal omega t plus c. So what is theta? Now theta is, so at the end of this integral, you can have to convert this back to the original variable. So theta is sine inverse of x divided by a. So let me rewrite it here. Theta is sine inverse of x divided by a, which is equal to omega t plus c. Then x equal, sine goes to the other side and multiplies by a. So let me write a, capital A. Sorry for that. So a sine omega t plus c. Now this equation describes the displacement of the simple harmonic motion. So you can see this is a sine function. Now what is this integration constant? Integration constant depends on the initial condition. What is the initial condition? That means suppose you start measuring the time of a particle moving in simple harmonic motion at a point somewhere here. So this will correspond to a different c value. If the motion starts from 0, this will correspond to a different c value, which is actually 0 at this case. So if you start from the greatest x, then it will correspond to a different c dash. We don't know what it is. So let me call it c2, this is c1 and 0. Now this equation describes the displacement of the particle in simple harmonic motion. Another equation would be x equal c sine omega t plus d cos omega t. This equation also describes the displacement of the particle. So we can use either of them to solve problem, but most of the times we are not going to use these equations. So there are simpler ways to solve problems. Right, so if c is equal to 0, you know the graph would be a sine function like this, and the highest values would be a and minus a. Right. So this function, so what does it tell us? It oscillates between a and minus a. So this is the displacement. This is actually what is happening in simple harmonic motion. So in simple harmonic motion, what we see is the displacement, a moving particle. We can't just we can't perceive velocity or accelerations. What we see is change in the displacement. So this is how the displacement varies. It oscillates with respect to time. Right.